就收起来就可以。对了 ，OK 了。品娟，哎，品娟，是你吗？还没写名字。
finish this first, and then I will discuss 6.2 and 6.3. We're most concerned with computing volumes. But first, so we want to compute areas between curves. We already last time saw how to do this. So you have two functions, f of x, larger equal than g of x, on AB. We usually require that the functions are continuous. Then you plot the two functions. Let's say this is the function g of x, and this is the function f of x. Then you see that there is an area. There's a region actually which is bounded above by f of x, bounded below by g of x, and we are between a and b. So this is the region. And for this region, we showed last time that in order to compute the area, what you have to do is you have to compute the integral. So the area is equal to the integral from a to b in f of x minus g of x dx. If you don't have this assumption, so if you don't, without this assumption, what you have to do is, so without the assumption, f of x larger equal to g of x, then you might have that there is also a region, but sometimes f is the upper boundary, sometimes f is the lower boundary. Then we also saw last time, so what you have to compute then is the integral from a to b, and it's the same integral, but only in the integrand you have in addition an absolute value. So this is then the way you compute the area between f of x and g of x. So the first thing usually you have to do is, because the first thing you have given is f and g, so what you should do first is to plot the functions. In particular, if the question if the problem only asks you to find the area enclosed by two functions, so find the area, it's actually the larger area, enclosed by y is equal to the fifth root of x plus 1 and the parabola x is equal to y squared plus 3y. So if you have an example like this, you first have to plot it, which in this case maybe is not so easy to plot because the functions are not too complicated, but it's hard to make a nice plot here. So the root is, so in one point is minus 1. It's the fifth root, so it looks a little bit like the third root, but it's only flatter. So it's this. That's the fifth root of x plus 1. And for this function, this is a parabola, but with respect to the y-axis. If you write it in this, you can write it in this form, but then it's clearer how it looks like. So it looks like, but actually, if you have access to a grabbing device, it's better to plot this with a grabbing device. So this is x is equal to y squared plus 3y. So what the example asks you to do is to find area of this region, because that's the large one. There is also a smaller one. The main difficulty here for this example is probably to find the point of intersection, because you can, if you solve this for x, you get x is equal to y to the power of 5 minus 1. And if you equate them, you have the equation y to the power of 5 minus 1 is equal to y squared plus 3y. That's a little bit awkward because that's an equation of over 5. So in order to solve this, you need some numerical computation, if you carry out the computation for either one of those integrals, so what you end up with is 4.28. So that's the area of this one. So you see for this example that sometimes it makes sense to actually interchange x and y. If we integrate over x, then this means we have to go from here to here. The upper limit is the red curve. The lower limit is the upper boundary is the red curve. The lower boundary is the yellow curve. But if you look at it in terms of y, then we integrate from here to here, and then the upper boundary is now becomes the yellow curve, and the lower boundary becomes the red curve. So we interchange them. Sometimes this makes a considerable difference. Sometimes the integral over x might be rather complicated, but the integral over y is much easier. Here actually this is not so hard to integrate, because how do you integrate something like this? You use the chain rule. You use the substitution rule. You substitute t is equal to x plus 1. Then it's also easy to integrate. So maybe let's look at one more example where it also makes more sense to integrate with respect to y, not with respect to x. So here compute the area between the parabola equation is given by 2x is equal to y squared minus 4, and the line y is equal to minus 3x plus 2. So again, we should plot the picture first. First parabola. You see, at y is equal to 0, x is equal to minus 2. That's also the lowest point of the parabola. Okay. And then at x is equal to 0, y is equal to plus minus 2. So this function looks like this. That's the parabola, right? 2x equal to y squared minus 4. Then we also have this line. So it's x is equal to 0, y is equal to 2 from here. And it's if we need on the points of intersection. This one we already have, so this one is the point 0. We need the other one. So for this you only have to, for instance, you express this in terms of x. So x is equal to y minus 2 divided by minus 3, which is minus 1 over 3. Y plus 2 over 3. And then you equate that. That's the best choice for you. Minus 2 over 3. Y plus 4 over 3 is equal to y squared minus 4. So you get the equation minus 2y plus 4 is equal to 3y squared minus 12. So 3y squared plus 2y plus 2y minus 16 is equal to 0. So you get the solution y is equal to minus 2 plus minus and the square root of 4 plus 12 times 16 divided by 6. And if you compute it, then you get minus 8 over 3. So one is minus 8 over 3, and or the other one we already know. The other one is equal to 2. Yes, because this is 40 over 8 plus 49. The square root actually can be computed 2 times 14. 14. Yes, this square root is 14. And then minus 2 plus 14 is 12. So 2 is one of them, the other one is this one. Because it's minus 2 minus 14, which is minus 16. So it's minus 8 over 3. Yeah. And actually, I don't need the corresponding, I don't really need the corresponding x value, because here it's obvious that it's better to set up the integral as an integral with respect to y. Because if you integrate with respect to y, you have to go from this point to this point, and the upper boundary of the region is always the red curve. The lower boundary of the region is the yellow curve. If you would integrate with respect to x, then you have to go from minus 2 to this point. But actually you have to divide the integral into 2 parts, namely from minus 2 to 0, because here the upper boundary of the region is the yellow one, and the lower is also the yellow one. And from here to here, because here the upper boundary is the red one, the lower is the yellow one. So it's actually less convenient here to integrate with respect to x. It's much better to integrate with respect to y. So the area. Maybe let's write down the point. So the point here is the y coordinate is minus 8 over 3. And the x coordinate, I get it for instance from this one, so it's or this one, minus 8 over 9 plus 2 over 3. So it's 13 over 9. So it's 14 over 9. So the integral now, in order to compute the area, is the integral from minus 8 over 3 to 2. And then the upper boundary is the red one. We have to express it in terms of y. So it's minus y over 3 plus 2y over 3. And the lower boundary is the parabola, which is given by this equation. So y squared minus 4 divided by 2 dy. Okay. And then you do the computation. And I did the computation. Why do I have two answers here? I'm not sure which one is correct, but it's 29. I'm not sure whether the because I have two answers to it, I'm not sure which one is the correct one. But you can do the computation on your own. It's not very complicated, it's just a polynomial which you have to integrate. It's just tedious work. I'm not going to carry it out. But maybe it's interesting to compare. If you do it with respect to x, then it's actually much more complicated because you have to go from -2 to 0. And then the upper, so you have to solve this for y. So the upper curve is now the square root of 2x plus 4 minus the lower one is minus the square root of 2x plus 4. This would be from here to here. And then you have to integrate from 0 to 14 over 9. And now the upper boundary is the red one, so it's minus 3x plus 2. And the lower boundary is the yellow one, so it's this one. It's plus square root of 2x plus 4. And if you compute this integral, you will get the same value as here. But you see, it's more. It's certainly better here to integrate with respect to y, not with respect to x, because this makes the situation easier. Which in some sense is clear anyway, because the problem comes from the way the parabola is given, because the parabola is given as a function in y, not a function in x. So because of this already, it's clear that you should go with respect to y, because the other is just a line. For a line, whether you express it as a function of x or a function of y, in both cases it's rather simple. But here, if you express this as a function in y, you get the square root, which is not really a problem. Of course, you can solve it. But what is the bigger problem is that you have to, if you go over x, if you integrate over x, you have to break the region into two parts, and you have to do two integrals. Certainly more work. And if the functions are more complicated, then it might be that only one of the two ways really works. The other one is maybe too complicated. Maybe also leads to much more complicated integrals to solve, which is not the case here, because integrating polynomials and integrating root functions is not very complicated. If what is inside the root function is just a linear function. Okay, but this is actually not very complicated. The only thing you have to do first is you have to carefully plot the two curves in order to figure out how the region looks like. And once you have a good picture, the rest is usually rather simple. Okay, so this was section 6.1 in our textbook. Now the next thing I want to discuss are volumes. Any questions to this? Here it's actually good if you have access to So the next application of the integral we want to give is volumes. So now the problem is we have a solid in the space. We have an object in the space. We want to compute its volume. Okay? And for this you can also, it's also possible to use a Riemann integral. We first have to figure out how. Because because we have to set up a limit of a Riemann sum. We have to express the volume as a limit of a Riemann sum. Then we can indeed use an integral to compute it. So for this we have to break the original object. We have to break it into simpler pieces where we can compute the volume. We need the same for the area problem. So we have to compute the area. What did we do? We inscribe rectangles. Okay. Because for rectangles it was clear how to compute the area. And then we had some limiting process in order to get the area. And because of the limiting process, the limit of the sum of rectangles is led to the Riemann integral. Because the sum of rectangles, this is a Riemann sum. Okay. So we need here something different, similar. So we have to approximate the solid by something which is easier to compute. Okay. Now, something which is easier to compute, solids for which it's easy to compute the volume are cylinders. Okay. Because a cylinder is actually something not really three-dimensional, something two-dimensional. A cylinder in its usually what you think about if I say cylinder is this here. This is called a circular cylinder. That's one type of cylinder. It's called a circular cylinder. There are other types of cylinders. For instance, this is also a type of cylinder, which is called the parabolic cylinder. So in general, what is a cylinder? A cylinder is you have some region, plane region. So here the plane region is bounded by a parabola. Okay, so here you have this plane region, or here you have the sort of disk. So this is called the P1, and I call this P1, and this I call also P1. And you have another plane region which looks the same, which is parallel to it, and here. Okay, and everything which is in between, that's called a cylinder. Okay, so a box actually is also a cylinder, because a box has a rectangle, okay, and another rectangle which is parallel to it, and everything which is in between. Okay, that makes up the box. Okay. And for a cylinder, so you have some base region. And the cylinder in general are all the points between two parallel copies of D of this. Okay. Now the reason why I say is so this is called a parabolic cylinder because B is a parabolic region. Now the reason why I start with these objects, cylinders, is because for cylinders it's easy to define the volume, to compute it. Because a cylinder is essentially something two-dimensional. between your textbook, because now we are talking about things in the space. Okay, so it's one of the difficulties of solids in the space is how to visualize them, how to draw them. Okay, that's why I'm using the slides from the textbook. So here, the blue thing is the solid, the given solid. Our goal is to compute the volume of this solid, or actually to define it, because so far we haven't even defined the volume of this solid like this. Okay. Now, what we have given is, so first we place it into the coordinate system. That's what happens. You don't see the z-axis. There is also the z-axis, which would point in this direction. So you only see the x and the y-axis. Okay. But you take the whole solid and place it into the coordinate system, in the Cartesian coordinate system. So we assume it's between A and B. In terms of x, you have placed it between A and B. Now what you do is you slice it with planes, okay, which are the planes have to be perpendicular to the x-axis. Okay, you see a plane here, this plane P. This is perpendicular to the x-axis. If you slice it, like you use a knife and slice it, what you get is what is called a cross section. The cross section of the solid. Now, what we have to assume is, in order to be able to compute the volume, what we have to assume is that we know the area of the cross section. So this is a function, a of x. Okay, so a of x gives you the specific point x between a and b, the area of the cross section. So it's a function called a of the capital A of x. Once you know this function, you have to compute this function first, which is the area problem which we can solve. Okay. Solving the area problem for any plane perpendicular to the x-axis between a and b, slicing the solid, we get this function a of x. So let's assume we have this function a of x. Okay. Then how to use it in order to compute the volume? So that shouldn't be too complicated. So what we do is we divide the interval from a to b into subintervals, as we did for the area problem. Okay. So for instance, this is the ith subinterval. Okay. Then what we would like to do is only for this part from xi minus 1 to xi, we would like to replace the solid, okay, so between here and here, by a cylinder. Because for a cylinder we can compute the volume, right? So the height should be the length of this interval. Okay, but what should be the base region? Because we could slice it at different points. We could use cross sections at different points. So we have to pick inside the interval a center point. And at this center point, we consider the cross section at this center point, which is the purple one. So this is just the cross section at the center point, xi star. Okay. And then what we do is we take this as the base of the cylinder. Okay. And the height of the cylinder is just the length of this interval. So on every interval we replace the solid by the cylinder, which you see over there. Okay. And then we just add up the volumes of the cylinder. And then again we let n tend to infinity. So we make subdivision here smaller, finer and finer. And in the limit we will get the volume. Right? So everything can now be expressed in terms of this function a of x. Any questions to this? I will write it now down on the blackboard. Unfortunately, I would like to keep this and write it at the same time. There is no other, it's exactly the middle, which is a little bit blackboard. Be here, would be much better. Yeah, it's the way it is. place the solid into the coordinate system. Such that it's between, in terms of x, it's between a and b. Then this a of x was the function we just saw. So that's the area of the cross section. Of S. At x, well, what I mean is you have a plane which is perpendicular to the x-axis. Okay. You slice it with a plane which is perpendicular to the x-axis. And a of x is the area function. Okay. Then what you just saw is, so we divide the interval AB into n pieces. Okay. The subdivision is such is so that xi is equal to a plus I times delta x. Okay. And then we choose a central point in the I subinterval. Then the volume of S is approximated by the sum of the volume of cylinders, the cylinders you just saw. Okay. So in every subinterval you take as region the cross section at the central point. The area is given by A of A evaluated at the central point, and you multiply it with the height of the cylinder, which was that x. It's the length of the subinterval. So really the volume should be the limit as n tends to infinity, and then I from 1 to n, A at the central point, delta x. Okay, you see this is a Riemann sum, so this is just the integral from A to b A of x dx, which is kind of clear anyway, because A of x is the that's the problem. You see, this A of x, this was the area of the cross section, right? And I just claimed that the volume is the integral from A to b of A of x dx. So that's kind of, if you think about the integral as a sum, which is the limit, it's actually a limit of a sum. Okay? But you can think about it as a sum. So what you do is you just add up all those areas, okay, from A to b. That should be the volume, right? And you multiply is kind of the height. So ax times dx is also the volume of a cylinder, but a cylinder which has a space region is a purple region and which has a very, very small height. That's why you multiply it with dx, and then you sum up of all of them. That's the integral. So the formula actually is clear. So for instance, you can apply this now to the. For instance, you can apply this to the sphere. If you wanna know the volume of a sphere, general sphere, what you do is you place the sphere into the coordinate system such that the center of the sphere is at the origin. Again, this is actually the three-dimensional coordinate system. Here you just see the xy plane. Okay. But there is a third axis. And then again you slice it. You have to compute first a of x, then you have to integrate a of x. That's the way you have to do it. If you slice it, what you get, of course, is the disk. At some point x, the radius of the disk will be the square root of r squared minus x squared. Because this here is given by the radius is r, so it's x squared plus y squared is equal to r. So this radius here is the square root of r squared minus x squared. And we know how to use the area of the disk, just pi times the radius squared. Okay. And then you add them up. So you integrate from minus r to r. Okay. That should be the volume of the sphere. Or in terms of the Riemann sum, that's what you do. You break it into pieces, and for every piece you use the cylinder. Okay. Here it's really a circular cylinder, okay, to approximate the volume. So the sum of the volumes of the cylinders will approximate the volume of the sphere. So here 5 cylinders are used. I don't know what the radius is. It's not written here. A radius is 1. So if you add up the volume of those 5 circular cylinders, you will get this approximation. And if you use 10, you will get a better approximation. If you use 20, you will get this one. And eventually, in the limit, this will give you the volume of the unit sphere. This method of computing the volume is called the method of cross sections. Because we use cross sections in order to compute the volume. So the example I just showed you is compute the volume of the sphere. Compute the volume of the sphere of radius r. Okay, so if we place it into the coordinate system and just plot the projection onto the xy plane, okay, then what we see is a circle. Into the circle, x squared plus y squared is equal to r squared. So essentially what we have here, so now we can look at our cross sections. So what we have here at x, the cross section at x, that's what we just saw, would be a disk. Okay. So the function a of x, okay, will be what? Would be that's the area of the cross section. Okay. The radius, I just said, is the square root of r squared minus x squared. So it's pi times r squared minus x squared. Okay. And then the volume is just the integral from minus r to r. And then a of x dx. Okay. So this is just 2 times pi times the integral from 0 to r. And then r squared minus x squared dx. And if you compute this is 2 times pi. And then r to the cube minus r to the cube divided by 3. Okay, so it's the usual formula for the sphere, which you learned in junior high school or high school, I don't know when. This actually, the sphere is a special solid because you can get it by rotating the upper semicircle. So you can take here, you can take the upper semicircle, right? Take the upper semicircle, like this here. This area below the upper semicircle and above the x-axis. You rotate it about the x-axis. Then you get the sphere. So the sphere is a special solid because it can be obtained by rotating a plane region. And solids like these are called solids of revolution. Solids which are obtained by rotating a plane region about some axis called solids of revolution. If you have a solid of revolution, if the solid is obtained by rotating a plane region about some axis, then it's very easy to use the method of. Usually, it's very easy to use the method of cross sections to compute the volume. Look at another example. Find the volume of the solid obtained by rotating the region enclosed by y is equal to x squared and y is equal to x about the x-axis. Okay. So the first thing you should do is you should make a plot of the region. Okay, so the region is actually, so this is the function y is equal to x squared. And then the line y is equal to x. So the region is this region here. That's the region enclosed by those two. Here, this point is 1. And we rotate it about the x-axis. If you rotate this about the x-axis, what you get is is a solid. Okay. As I just mentioned, this is called a solid of revolution because it's obtained by revolving something around some axis. And for such solids, it's actually quite easy to use the method of cross section. You only have to figure out how does the cross section here look like. So the cross section here because if you consider a certain point x, okay, so what you get is here is a circle, and then here you have another circle, and then everything which is in between, that's the area of the cross section. So this here is called a washer, something like this. Okay. So it's for the sphere, the cross sections were discs. Here are washers. So they are washers. But it's easy to write down the area of the cross sections. It's just pi times the outer radius is x squared minus pi times the inner radius. The outer radius is x. The inner radius is x squared. Okay. So that's the disk with radius x, and that's the area of the disk with radius x, and that's the area of the disk with radius x squared. It has to be subtracted because that's the whole. So the volume is then just the integral from 0 to 1, and then I take out the pi, and then it's x squared minus x to the power of 4 dx. That's of course easy to solve, it's just pi. Then the antiderivative is x to the cube over 3 minus x to the power of 4 over 5, evaluated at 0 and 1. So it's just pi, maybe I use bracket here, so it's 1 over 3 minus 1 over 5, which is pi, so it's 15, and then 5, 2 pi 15, 2 pi divided by 15. Okay, so that's the volume here of the solid of revolution from this question. Of course, one could also rotate about another axis, not necessarily the x-axis. One can also rotate, for instance, about the y-axis. One could also rotate about any other line. So compute the volumes region enclosed by y is equal to square root of x and y is equal to x squared is rotated about the y-axis and the line x is equal to minus 1. These are actually two different solids. So that's why I say the volumes, because these are two different solids. Again, if you plot the region, okay, so y is equal to square root of x and y is equal to x squared. Again, here is 1. Now we rotate about the y-axis. Okay, that's the first solid, and the second solid we rotate about the line x is equal to -1. That's another solid. Now, in both cases, if you rotate about the y-axis or this line, the cross sections. Now we should do the cross sections with respect to the y-axis, right? Because that's where the rotation takes place. Okay, so we should slice like this. Okay. In both cases, they are again washers. So in the first case, so this is the outer radius, this is the inner radius of the washer. But we have to express it in terms of y. So pi times the outer radius is the square root of y, so it's y minus, and the inner radius is y squared, so it's pi times y to the power of 4. So that's in the first case. Now, in the second case, actually you also have this distance 1 here in addition. Okay, so the outer radius is 1 plus square root of y squared, and the inner radius is 1 plus y squared. Everything squared because it's the radius. Radius squared times pi. That's the area formula for the area of the disk. Okay, so that's for the second one. If you rotate about -1. Okay, so the volume, the first volume is you just have to integrate from 0 to 1 a of x dx. I'm not going to do the computations. The computation is easy anyway. 3 pi over 10. And for the second one, a little bit more work is needed. It should be A1. If you do the computations, what you get is 29 pi over 30. But you see that the point should be if you have a area, if you have a solid of revolution, it's usually easy to compute, to use this method of cross sections. But not all solids are solids of revolutions. There are also solids where you still can use the method of cross sections, but they are not solids of revolution. For instance, if you have to compute the volume of a pyramid, okay, a pyramid is not a let's say the base of the pyramid is a square. Okay. A pyramid is not a solid of revolution. So if you have a pyramid, let's say height is h, and the base is a square of radius of side lengths L. Now for in order to compute the volume, you can still use the method of cross section, but this is clearly not a solid of revolution. It is not generated by revolving a plane region about some axis. But again, you can place it in the coordinate system, and then compute the cross sections, and then just integrate over the cross sections. I will show you this after a break, so let's make a break of 10 minutes. Then I will show you how to compute the volume of the pyramid. Okay, so let's go on. Let's finish this example. So, as I said, not all solids are solids of revolution. This is an example. So but here we can still use the method of cross sections. So how to use it? You first place it into the coordinate system. For instance, of course you have different ways of doing this, but let's fix the coordinate system such that the x-axis just passes right through the. I'm sorry, it's a little bit. It's not very nice picture. So this, but the x-axis passes right through the pyramid, and the highest point of the pyramid is in the origin of the coordinate system. So then if I plot the projection onto the xy plane, so what I see is just a triangle like this, where this here is L, and this here is the height. And now the cross sections. So if I look at some point x here, x is y. So the cross sections are just squares, right? Cross sections are just squares. Let's say the y here is also this, not only the upper part. Okay, at point x. But it's, of course, it's easy again to write down a of x, okay. Because you can compute. There is a relation between x, y, h, and l, as you know, because you have here two similar triangles. So x divided by h is equal to y divided by l. So you see that y is equal to x divided by h times l. Okay, so, and the y is the side length of the square, so it's just the a of x is just y squared, so it's x squared divided by h squared l squared. And in order to compute the volume, you just now integrate over the area of the cross sections. So the volume is just the integral from 0 to h of a of x dx, which is the integral from 0 to h, and then x squared. The function is x squared. The rest actually doesn't depend on x, so I can put it in front of the integral. So it's L squared divided by h squared, and then x to the cube over 3 at 0 and h. So what you get is L times h, L squared times h divided by 3. That's the formula for the volume of the pyramid, which you also learned in junior high school or high school. It's actually quite easy to derive using, again, the method of cross sections. Here's another example from the textbook. Wedge is cut out of a circular cylinder of radius 4 by 2 planes. Cut out of a circular cylinder by 2 planes. planes is perpendicular to the axis of the cylinder. The other intersects the first at an angle of 30 degrees along the diameter of the cylinder. So one plane is perpendicular to the axis of the cylinder the other intersects the first at an angle of 30 degrees. Angle of 30 degrees along the diameter. Along the diameter. Find the volume. Of the wedge. Usually the only problem is how to place it into the coordinate system, and then how to intersect it with planes. So which kind of cross sections to use. So we have a circular cylinder. Now let's assume that this is the x-axis. This is the y-axis, and this is the z-axis. And let's assume that because we use two planes in order to cut out the wedge. One plane is perpendicular to the axis of the cylinder, so we can assume it's the xy plane. It's cut here, and then it's cut with a second plane. And the second plane intersects the first one at an angle of 30 degrees along the diameter of the cylinder. So it's like a plane like this. Okay. The diameter. If the first plane is the xy plane, then the diameter is here. So let's assume like this. So what we get is here is some path. And the wedge is what you see here. So that's the wedge, which is cut out by the. So this piece here. This is the upper boundary of the wedge. This is the upper boundary of the wedge. The lower boundary is on the xy plane, and everything which is in between. So we have to compute, and we know the angle. We know the angle between this and the xy plane is 30 degrees. So now the cross sections, I also want to use cross sections perpendicular to the x-axis. So I slice it like this. Okay. So if I slice it like this, what I get, there is a much nicer picture in the textbook. So if I slice it at a point like this, so what I get here is this is my point. So what I get here is a triangle. It should be a right triangle. The cross sections here is a right triangle. finals. Where? Because the base circle has the equation x squared plus y squared is equal to the radius should be 4. I forgot to say this in example. So it's equal to 16. Okay. So that's so this length here is just the square root of 16 minus x squared. So here you have the square root of 16 minus x squared. Okay. And you know that this angle here is 30 degrees, pi over 6. Okay. Now it should be easy, right? Because the tangent of pi over 6, you need also this length here. The tangent of pi over 6, let's call it s. So this is equal to s divided by square root of 16 minus x squared. So you get that s is equal to the square root of 16 minus x squared. The tangent of pi over 6, the sine of pi over 6 is 1/2, and the cosine of pi over 6 is 1/2 multiplied with the square root of 3. So divided by the square root of 3. Okay. So the cross section, this is this yellow rectangle. So this is the cross section. This is a of x. The area of this one, the area of this one is a of x. So a of x is equal to this one multiplied with this one divided by 2. So 1 over 2 times square root of 3, 16 minus x squared. Okay. Formula for the area of the right triangle. And then the volume is just the integral from minus 4 to 4. And then 1 over 2 times square root of 3, 16 minus x squared dx. Okay, and easy to compute now. This. Just the numbers are not very pretty, so it would be 128 over 3 times the square root of 3. So usually the first thing you have to do if you have an example like this is you should have a good picture. Okay, because you have to place the solid into the coordinate system, you have to decide how to slice it, because you could also slice it like this. Okay, but this, if you slice it with planes parallel to the perpendicular to the y-axis, okay, the cross sections are more complicated to compute. Okay. If you slice it, you could also slice it with planes which are parallel to the xy plane. It's also rather awkward cross sections because it would be some part of the circle. But if you slice it like this, at a certain distance, you would get some part of the circle. That's maybe not so convenient to compute. If you slice it parallel to the xy plane, I sliced it with planes parallel to the yz plane. Okay. If you slice it with planes parallel to the xz plane, also with cross sections are not so easy. So first you have to place it into the coordinate system, and then once you have placed it into the coordinate system, you have to decide how to slice it, the direction. There are usually 2 different directions: perpendicular to the x-axis, perpendicular to the y-axis, or perpendicular to the z-axis. Okay. But eventually you have to figure out this function a of x, the area of the cross sections, and then the rest is just straightforward computation. Sometimes this example can be rather tricky. For instance, a tricky one. Usually, the reason why these examples are tricky is because some of them are hard to visualize. For instance, find the volume
solid obtained by intersecting the two cylinders x squared plus c squared is equal to r squared and y squared plus c squared is equal to r squared. That's a little bit hard to visualize, hard to plot how this solid should look like. If you just plot the projection onto the xy plane, then so for instance, how this solid is now just okay, this here is r, this is minus r, and you rotate it like this. You have to think about this. Rotate it like this. It's the projection onto the xy plane. So this one is like this. Rotate it like this. The other one is like this. So it's that's the other one. Now you see nothing, right? Because it's not three-dimensional. So it's one is like this. The other one is like this. What is common to those two? It's hard to plot. In the textbook, you have a picture. I'll show you this one. This was the example I just showed you before with the wedge, right? So that's a much better picture than the picture I plotted on the textbook. You see, I tried to plot the same, but it's prettier, right? It's also clearer here that okay, these are rectangles. This is the yellow rectangle which I plotted. That's a nicer picture. Here you see these are the two. These are the two cylinders. Here you have one, the blue one and the yellow one. And if you intersect them, you get this kind of this object, this solid. Now, how to compute the volume of this one? Okay, so think about the coordinate system. It's like here's the xy plane, and then the z axis is like this. So the z axis comes out from this from the intersection of the two. Surfaces, which you see the blue one and the yellow one, and now you have to find cross sections. Okay. If you slice it, for instance, like this, you slice it with a plane like this. So if you cut down a piece like this, that's rather complicated cross section because it looks like this, and here's straight, but it looks like this. The main observation you have to make is you have to slice it with planes which are parallel to the xy, which are like this. You have to slice it like this, because then you get only squares. Okay. So what you have to figure out is so what is the side length of the square? This is a better picture. The coordinate system is missing here in this picture. Better picture than the one I showed you. This picture kind of doesn't tell you a lot, right? But So now we understand. So this is one solid, right? This is the other solid. So what you have is, what is important here is, what you have is something like this here. Okay, now it looks even more ugly, but you see, it's going down here, and also it's going down here, right? You have to take it here, and you have to move it upwards. Okay, where this here becomes something like this, and this becomes something like this, and this is one part. So because here there is a, this is one cylinder, and this is one part of this cylinder. This is another part. This one and this one, and those two faces are from the other cylinder. You can imagine it? No. Maybe once more the three-dimensional picture. I'm sorry, I should plot it here maybe. This, what I see here is I look at it from above. Okay, and so this one and this one are the two yellow surfaces, and this one are the two blue surfaces. I look at it from above. So you have to take this point in here and you have to move it in this direction. That's half of it. Like this. And now you have to, so certainly we should slice it like this, right? So certainly, so then what you get as cross section is something like this, depending on the height where you slice. It's just a square. Moving up to just this point, and here you have the whole thing. It's like slicing it like this, different heights. So what you have to figure out is what is this length here? That's the only thing, so I'm integrating with respect to C. So you have to find out, okay, so what is A of C? A of C is, if you know that this here is A, then it's A squared. A depends on C. Okay, so what is A? Okay, so now we saw it twice, so now we know how it looks like. So what is this A? What is this the side length here? What you see, if for instance, if I plot the projection, just the upper part on the y-axis. So what you have here is actually a circle, right? So for this one you have a circle like this. So here that's y. Let's see now. So it's c squared plus y squared r squared. And what I plotted here, you have it here. Okay. Now it's clear, right? What so you just solve it for y. So y is equal to r squared minus c squared, and the square root plus minus. So it's this. But what I wrote here is just this length. And A is twice this length. Okay, so A is, so this is y here. A is twice y. So it's twice. So A of C So A of C is the square of it, which is good because then the square root is gone. So it's 4 times R squared minus C squared. And now it's just, and the volume is just the integral from minus R to R of A of C, which is 8 times the integral from 0 to R because of symmetry. 4 from here, and then if I replace this by 0 to R, then it's because from 0 to R is the upper half. From minus R to 0 is the lower half, twice. So 8 times, and then R squared minus C squared. Easy. So you see, it's actually very easy to compute. So this is 8 times R to the cube minus R to the cube divided by 3. So the volume is just 16 R to the cube divided by 3. That's a rather tricky example because it's very hard to visualize it. And in the textbook there is an even trickier one, namely 3 cylinders. You have 3, not only 2. You have 3 meeting at a certain angle, and then what is common to them, the solids, the volume you should compute. That's even trickier. Okay, but this is maybe from the examples in section 6.2. This is maybe the most complicated one. The other ones are all they're rather easy, or some of them are also slightly tricky. But this is the hardest one because it's very hard to visualize it. But in the textbook, the figure you just saw, you also have it in the textbook. But the final computation, once you figure out how to do it, the important thing is you have to slice with planes parallel to the xy plane. Okay, because the cross sections are in particular easy if you slice with planes parallel to the xy plane, just squares. If you slice with other planes, it's more complicated. Also computable, but more complicated. You don't. That's the good thing about this method of cross sections. You can decide which direction you slice. Okay. Also, you can decide how to place the solids. So you should place it and slice it so that life becomes easy. Okay. Now, I emphasize that this method is called the method of cross section. So because of this, you maybe already guessed that there should be another method, okay, which is called the method of cylindrical shells. Now, why is another method necessary? Because there are certain examples which look also pretty easy, but you run into a problem if you want to use the method of cross sections. Namely, consider the following solid of revolution obtained by so this is the function. This is the function 2x squared minus x to the cube. This point here is the point 2. Because you see at 2 this function is 0. At 0 this function is 0. At 2 the function is 0 as well. Okay. So from 0 to 2 this function is non-negative. If you plot it like this, then there is a region here. Okay. Now assume this region is rotated about the y-axis. This gives you, again, a solid of revolution. And what we would like to do is we would like to compute the volume of this solid of revolution. So you take this region, you rotate it about the y-axis. Gives you a solid. And this solid looks like you take this one and you rotate it, right? And you would like to compute the volume of the resulting solid. Now you can say, okay, it's a solid of revolution, so I can use the method of cross sections. So what you have to do is you have to so you take an x value. If you not an x value, a y value. If you rotate it, you get again the washer, by washer. Something like that. If you rotate it, so it shouldn't be not too hard. It should not be too hard to compute the area. But provided you know the inner and outer radius of the washer. But in order to know the inner and outer radius, you have to solve this for x. But it's a cubic equation. Okay, so that makes it complicated here. It's not impossible if you have a computer algebra system like Mathematica or Maple. You can just give the program this function and the software can solve it for x. That some ugly expressions, okay. And then you can use the method of cross sections. But the problem is because we haven't learned how to solve a cubic equation. We haven't learned the solution formula. Okay, so we cannot really solve for x. It's a very easy function. Okay, so but the method of cross sections doesn't seem to work here. So another method, the problem is really that you want to integrate with respect to y. Okay. Another way would be to we could try to find a way of computing the volume, but by integrating over x. And this will lead to another method, which is called the method of cylindrical shells. So if you have a function which is non-negative, and x is between a and b, okay, then you have the same problem. So a. This is my function. Okay, again, I have a region here. This is the usual region below the function and above the x-axis. This is the y-axis. I want to rotate it about the y-axis. So what I can do is I can just divide the interval AB into n pieces. So that's the usual way to do it. Okay, so let's say this is xi minus 1. This is xi. Okay. So I have then xi is equal to a plus I times delta x. I choose again a sample point in the i's subinterval. Okay, so I choose a sample point, and then I have here, a rectangle. The rectangle has length delta x. So this length here is delta x. The height is the function evaluated at the sample point. So this here should be. I should try to close this. Okay. So this is the sample point here. So that's the height then. Now if you take this one. If you rotate this, only this piece about the y-axis, what do you get? You get a circular cylinder with a hole drilled out in the middle. Okay. That's called cylindrical shell. So you get a circular cylinder but with a hole drilled out in the middle. So let's assume that this radius here, the outer radius is R1, the inner radius is R2. Then the volume, you need the volume of this piece because you add up the volumes of those pieces if you do this for every interval. And then you take a limit, and this should also give you the volume. Okay, so the volume, this is called the cylindrical shell. So the volume of the cylindrical shell is just, you compute the volume of the circular cylinder and subtract the volume of the hole. Okay, so this will be equal. If I simplify this a little bit, it will be equal to this one. Now, whenever we see something like a squared minus b squared, we think about a minus b times a plus b. So I can write this as 2i, then r dash h, and then r2 minus r1, where this, maybe I already maybe I do solve it. So this will be r1 plus r2 half, and then h, and then r1 minus r2. This we call delta r. This is the thickness of the shell. Okay, this is from here to here, the thickness. And this here is the average radius, so I call this r prime. Okay, so the formula for a cylindrical shell is the circumference of the circle using the average radius multiplied with the height multiplied with the thickness of the shell. Okay, that's the formula for the. Now the volume here. The volume of the solid in question should be the sum I from 1 to n. Okay. The sum over the volumes of those cylindrical shells, which I get here from this picture. If I do this for every subinterval. Okay. And for this piece, this is the ith piece here. For this piece, the contribution of this piece, if I rotate it, is given by, so it's 2 times pi times the average radius, which is here, with average radius is just so for the sample point here, I shouldn't choose any sample point. I should pick xi prime to be equal to the midpoint of the interval, because that's then exactly the average radius. Here I have the average radius, and then multiply with the height. The height is, because if I choose a different sample point, I would have here the function evaluated at something different, not at the same point as this one. Then it wouldn't be a Riemann sum. And then multiply with the thickness. The thickness is just delta x. Okay, so that's what I get if I rotate those pieces. If I divide the interval AB into pieces, for every piece I use a rectangle, I rotate the rectangle. And I get a solid which approximates the solid for which whose volume I want to compute. Okay, and the volume will be approximated by the sum of the volumes of those cylindrical shells. That's what I just brought down, and that's exactly a Riemann sum. So and then we take limit. So in the limit, what I should get is the volume. Strictly speaking, that's something I have to prove now, because I defined the volume, maybe by the method of cross sections already. Okay, so I have to prove now that this gives the same result. But that's not so complicated to prove. Okay, and you see this is a Riemann sum. So what I have to do is I have just to integrate from a to b 2 pi x f of x dx. That's what I have to do. This is called the method of cylindrical shells. This formula is easy to memorize because you see, if I look at some point x, if this is my point x, for the point x, this piece is rotated. Okay, and that's also a cylindrical shell, but with a very small thickness. Okay, so by the formula, what I have to do is I have to if you think about this piece, if this piece is rotated, okay, this piece gives you a cylindrical shell with a very small everything taken out with very small thickness. You can just slice it open, stretch it out. Okay. Then if you do this, what you get is a rectangle. The height of the rectangle is just f of x. Okay. And the length of this side is just the circumference of the base circle, which is 2 times pi times x. Okay. So for this piece, you get 2 times pi times x times f of x. This is the area multiplied with the thickness, which is dx. Okay. So actually, this formula perfectly makes sense. And you add over all that. Okay. That's the one. You don't have to memorize this formula. It's easy to heuristically easy to find it. But this formula has the big advantage that we are now integrating over x. If you use the method of cross sections, you would integrate over y, which in the first example I showed you is not easily possible. So if we go now back to the first example I just showed you, now it becomes very easy. Okay. So the function was x 2x 2x squared minus x to the cube, and we rotated about the y-axis. Switched. Okay. Now it's very easy. So the formula becomes the integral from 0 to 2. This is the form 2, and then it's 2 times pi times x multiplied with the function, which is 2x squared minus x to the cube, and then dx. You don't have to solve for x anymore. Okay. And if you do the computation, you get some value 16 pi divided by 5. That's what you get for this example. So now for some of the examples we saw before when we used the method of cross section, you have another method which you can alternatively use, namely the method of cylindrical shell. Sometimes both methods can be used. Sometimes, like in this example, it's easier. One is preferable over the other. So in this example, the method of cylindrical shells is clearly preferable over the method of cross sections. Because for the method of cross sections, of course, you can solve it. If you can look up the solution formulas for the cubic equation, you could solve it for x. But the formula is rather, the expressions are rather big. Okay? And then the integration is also getting complicated because it's the integral over a complicated function. Then, so it's certainly easier here. Even so, there is a formula for the cubic equation. It's certainly easier to use here cylindrical shells. And if I have here a polynomial of degree 5, then there is not even a formula. Okay, then certainly you have to use the method of cylindrical shells, unless you just want to have numerical approximation of the volume. So how about, you can, of course you can also use this method if you rotate about another axis. X is different from the y-axis. Maybe let's go back to the example. Find the volumes obtained by rotating y is equal to x squared and the area enclosed by the region enclosed by y is equal to x squared and y is equal to square root of x about the y-axis and x is equal to minus 1. I did this before with the area, with the method of cross section. So if you use the method of cylindrical shells, this is y is square root of x. This is y is equal to x squared. You rotate, so first about the y-axis, then the line x is equal to minus 1. So before we integrated over y, now we integrate over x. That's the difference. Okay. So if you do this for the first volume, so if you rotate about the y-axis, so you only have to think about the integral goes from 0 to 1, so I fix an x value between 0 and 1, and then what I rotate is a line like this. I rotate it about the y-axis, which gives you, again, a cylindrical shell. The height of the cylindrical shell is given by square root of x minus x squared. That's the height of the cylindrical shell. And it's just the same formula. So it's the integral from 0 to 1, 2 times pi times x. X is the, this is the average, this is the circumference of the base, and then multiplied with the height, which is square root of x minus x squared dx. It's just the same explanation. So you have this, as I mentioned before. So you get something like this, which is very thin, which is hollow. You slice it open. You flatten it out. So here what you have is 2 times pi times x, and here you have the height, which is in this case square root of x minus square root of x minus x squared. Okay. And the area of this piece is this one, and this dx is coming from the thickness. And if you do the computation, you will get the same result as before. pi over 10. Now, if you rotate about the line x is equal to minus 1, what is different? It's still the integral from 0 to 1. You still integrate from here to here. Okay. And the height is just the same, but what is different is the length here. Okay. Because now the radius of this of the base circle now becomes you have to add 1 plus x. So it's 2 times pi times 1 plus x. That's the only difference. The rest is just the same. Square root of x minus x squared dx. And again, if you do the computation, you get the same value as before. Here, for this example, you can either use the method of cross sections, or you can use the method of cylindrical shells. Both of them work equally well here. But sometimes one method is maybe preferred over the others because the resulting integral might become much easier with one of the methods, okay, and complicated with the other one. So sometimes one method is preferred over the other. So these are the only sections I want to teach from chapter 6. Chapter 6 you have some further sections. I have 2 further sections. One is called average value of a function. One is called work, which is the work from physics. These are not part of those 2 sections are not part of the syllabus. So we saw essentially 2 applications of the definite integral. The first one was for computing areas between curves, and the second one was for volume. And for volumes we had 2 methods, the method of cylindrical shells and the method of cross sections. Before we can give more applications, before more applications can be discussed of the definite integral, we have to, because in order to compute the definite integral by the fundamental theorem of calculus, we have to compute the indefinite integral, which is just the antiderivative of the integrand. Okay. And so far we haven't discussed systematically how to compute the indefinite integral. Okay. And we have seen some methods, the substitution rule for instance. We also know that for the indefinite integral, the integral of f plus g is the integral of f plus the integral of g. Okay. But there are other functions where we haven't discussed yet how to compute the indefinite integral. More complicated ones. Here, today, the functions you all saw, either root functions or polynomials, they're easy to. For root functions and polynomials, it's easy to find the antiderivative. But you might have more complicated functions like logarithmic functions or inverse trigonometric functions and so on. So how to compute then the definite integral? That's the next topic we want to discuss. We have seen how to compute the integral of a sum, of a difference we also know. And we also know how to compute the integral of functions which are the derivative of composite functions by just reversing the chain rule. Okay, this was the substitution rule. But what we are missing is how to compute the integral, for instance, of the product of 2 functions. Okay. That's the first topic in chapter 7, which is called partial integration. So this will, in this, that's section 7.1. In this section we want to generalize, we want to find a suitable way of formula for computing the integral of a product. We will see there will be only a partial answer. That's why this method is called partial integration, because the integral is replaced by another integral, which might be easier. And then there is section 7.2, which is called trigonometric integrals. So in this, we will see that there is no for a product of 2 functions. It's the integral. You cannot write it. there is no for differentiation. If you have a product of two functions, there is a rule how to compute the derivative. But for the integral, for the indefinite integral, for the product of two functions, there is no rule which tells you how to compute the integral. This makes integration more complicated than differentiation. So in the other sections, then 7.2, 7.3, and 7.4, we will look at certain classes of functions, and we will discuss how to integrate them. Okay, in section 7.2, it will be trigonometric functions. So functions like sine to the power of 3 times cosine to the power of 5. How to compute the integral. That's in section 7.2. Then in section 7.3 we will learn a general method which is called trigonometric substitution. And in section 7.4 we will discuss rational functions. There is also a method called partial fraction expansion. And these are essentially the sections we are going to cover in chapter 7. Then in chapter 7 there will be one section left which is called the improper integral, which discusses something related but which is slightly different because it's a further extension of the notion of the integral. And this section, that section 7.8 will be the last one, then the course will be over. So for the remaining 3 to 4 weeks, that's what we're going to do. And we have the final also, which will be at the end of the month. I think I announced this already in the first lecture, so it will be on December 29th. That's still 3 weeks. 3 weeks, right? 2 weeks, 3 weeks ahead. There will be one lecture after in January, right? But then it will be over. And then you have to take the joint calculus exam, which is Saturday of the first week, the first or second Saturday in January. Still enough time. Okay, so there are still 4 minutes left, but I don't want to start with chapter 7 today, so that's it for today. Unless there are any questions. If not, that's it for today. Okay.
就卡上有改。专学。